What's going on, everyone? Welcome back. Patrick here, and moving on to the next video, another example dealing with the intermediate value theorem. So like I did in the previous examples, I'm going to take this problem here, take the parameters from it, and then apply it to the theorem, which I have written up here. So same process. If you didn't watch the previous videos, highly recommend you do watch them in order, including starting with the overview video, just because there may be explanations in those videos that I'm not going to cover in this example. So make sure you're exposing yourself to all the different problems that I present. So what do we have here? We have to show that this equation here has at least one real root. So exact same format as the previous example. We got the square root of x equals 1 over x plus 5. And as I mentioned in the previous example, a real root basically means the x value that will make the left side equal to the right side. So what you want to do is, first thing, bring everything over to one side, like I did in the previous example as well. So I'm going to take this 1 over x plus 5. Notice this is like a whole expression itself. You could think that there's like a positive in front. So when I bring it over, it's going to turn negative, right? This sign doesn't change here, right? That's the expression that we're adding. So when I bring over that expression, now we're going to be subtracting it. So I brought that over, and then what am I left with on the right side? I'm left with 0. That's always the format you want to get these equations in when you're dealing with the intermediate value theorem. Sometimes they'll be in this format, they'll be given in this format. A lot of times they won't be, and you have to put it into this format over here. So what we do then is we let this expression on the left side here equal a function. So we got f of x equals the square root of x minus 1 over x plus 5. And what we got to do is show that there's some kind of x value that's going to make the function equal to 0. That's going to make the function, this function, have a y value of 0. Another way to state this is to show f of x has at least one, right? At least one real root, or has at least one x-intercept. Same thing. The x value that makes a function equal to 0 is the x-intercept. And if we can show that this function has at least one real root, or at least one x-intercept, or an x value that makes the y value equal to 0, then that's going to be the same as the root of this equation. That same x value is going to make the left side equal to the right side over here. Okay, so what I want to mention here is that this function that we're working with, notice that it's a little bit more complex than the previous example. In the previous example, we had a cubic function, and we know the cubic function has a domain of XCR. You could plug in any x values and it won't make the function undefined. Notice that this function here, it has some restrictions on its domain. So it's not going to be continuous for all x values. And that's important because in order to use this theorem, f of x, this function that we're going to work with, has to be continuous on the interval that we choose. So what I want to talk about first is where this function is going to be continuous. So just by looking at it, notice how this denominator is going to be 0 when x is equal to -5, which would make the function undefined. So x cannot equal -5. You can see that from this expression, 1 over x plus 5. If we have -5, if we plug it in here, then this part is going to be undefined. But also notice that this expression, the square root of x, we can't square root a negative number. So from this expression here, notice that all the x values have to be greater than or equal to 0. So notice that x cannot just not equal -5. It can't equal any negative number. And so this restriction here is not relevant. We don't have to actually write it down just because it's part of this restriction here, where x has to be greater than or equal to 0. It can't be any negative number, not just -5. So even though, for example, if we plug in -2 here, right, we'll end up with -2 plus 5, so we'll have a +3 in this denominator. We can't plug -2 in here. So for the whole function, -2 won't work. So x has to be greater than or equal to 0. That is the domain for this function. So any interval that we choose when we apply this theorem, the intermediate value theorem, we're going to have to choose x values greater than or equal to 0. So f of x is continuous when x is greater than or equal to 0. Notice that any x value greater than or equal to 0 won't make this function undefined in any way. Right? So that is pretty important to know initially. Sometimes you got to figure out where's this function going to be continuous before you pick this interval here. Because you can't pick an interval where the function is going to be discontinuous or not even exist. Right? So we'll keep that in mind when we're picking an interval. So if you remember from the previous example, what do we have to do? We basically have to find two x values that have a positive y value and a negative y value. Why? Because if one of our x values has a positive y value, the other has a negative y value, then we know within that interval, since the function is continuous within that interval, it has to cross this x-axis at some point. And that would show that f of x has at least one x-intercept or one real root. Right? We have to show that it's going to cross this right here. And so from here, it's kind of trial and error at this point. You got to pick two x values. So the first x value I'm actually going to start with is 0. I usually start with 0, just a simple number to work with. If I plug in 0 for all the x's here, notice I'll have 0 minus 1 over 0 plus 5, which is 5. And 0 minus 1 over 5 is negative 1 over 5. So this function is going to have a y-intercept of negative 1 over 5. Now you don't have to necessarily pick an x value 0. You could pick other ones just as long as the two x values that you pick have a respective positive y value and a respective negative one. So we have an x value with a negative y value. This is actually where the function starts. Remember the domain, x has to be greater than or equal to 0. So let's pick another x value. Let's try to find another x value that's going to have a positive y value. And because we have this square root of x, I'm going to pick a number for x where that square root is going to be smooth. So let's do 4. So if I pick 4, what I'll end up having, we could actually, I just realized we could pick 1 as well. Anyway, let's just stick with 4. I'll do it down here. So f of 4 is going to be, square root of 4 is 2 minus 1 over 4 plus 5 is 9. So this 2 here, we can change to 18 over 9, get a common denominator. So we would have 17 over 9. And notice we got a positive y value, which is what we wanted. So at an x value of 4, this function is going to have a y value of 17 over 9. And now we can apply the intermediate value theorem showing that this function is going to have at least one real root or at least one x-intercept. Why? Because remember, the function is continuous for all x values greater than or equal to 0. There's not going to be any breaks here. So we know if it's going to go from this point to this point, at some point somewhere between 0 and 4, it has to cross that x-axis, right? So just knowing that, we can now take these parameters and throw it into this theorem. So given f of x is continuous on the interval where x is between 0 and 4, so we would write 0 here and 4. You may want to write the actual function up here as well. So you could say given f of x equals this function here is continuous on the interval between 0 and 4. I'm just going to leave it here just because I don't have as much room up there. So given f of x is continuous on the interval between 0 and 4, that's the a and b value that we picked, and f of 0 does not equal f of 4, which is true because f of 0 is negative 1 over 5, f of 4 is 17 over 9. If n is in between f of a and f of b, so the n value that we're working with is this 0 here, right? We're showing that there's at least one x value where this function is going to equal 0. So the n here is 0. If 0 is in between f of a and f of b, which it is because f of 0 and then f of 4, remember, f of 0, negative 1 over 5. F of 4 is 17 over 9. Notice that 0, this y value, is between these two y values. It's in between negative 1 over 5 and 17 over 9. Then there's going to exist a number c in between a and b. So in between 0 and 4, there's going to be some kind of c value or some kind of x value in between these, where f of c is going to equal n, and the n value in this case is 0. And if you write out this sentence here, after you've done all of this, after you showed all this work, then you are done the question. Because we proved with this theorem, right, the function is going to be continuous on this interval. And because there's a negative y value and a positive y value, at some point it's got to cross that x-axis. We're not sure where. Again, we're not finding the actual real root. We're just showing that there's going to be a real root. And we did that, and we showed that there's definitely going to be some kind of root between 0 and 4. So there's going to be some kind of x value between 0 and 4 that's going to make that original equation we have, the square root of x equaling 1 over x plus 5, that's going to make the left side equal to the right side.